Good day, everyone, and welcome to this Lightbend webinar for July 11th, 2019, titled Scala 3 is Coming, Martin Odersky Shares What to Know. My name is Oliver White, Chief Storyteller and MC at Lightbend, and joining me today is, as the bespoke title implies, a very special guest, Dr. Martin Odersky. I'm guessing that most of you know of Martin, but in case you don't, he is the creator of the Scala programming language back in 2003. He's also the author of Java C, a professor at EPFL in Lausanne, Switzerland, and the co-founder of Lightbend, along with Jonas Bonaire, the creator of Akka. And from my personal experience as the founder and father of such a popular and widely adopted programming language, I find Martin to be especially unique in the modern programming industry by remaining a highly engaged, visible, and approachable leader of Scala to this day. While I introduce today's session, which has a lot to cover and should last about an hour, I'd like to ask our audience a quick poll question. In Scala 3.0, I see myself using the following feature or features a lot. So as stated in the webinar title, Scala 3 is coming. In its first redesign since 2010, Scala 3 will be a big step toward realizing the full potential of these ideas, and will go into feature freeze later this year with plans to release Scala 3 in mid to late 2020. As Martin will show you, Scala 3 has a major objective of simplifying things where it's possible and making it easier for developers that have experience in other languages to get started coding in Scala in a more simple fashion. Specifically, Martin will review other goals like how to eliminate inconsistencies and surprising behavior in Scala, building on strong foundations to ensure that design hangs well together, consolidating language constructs to improve the language's consistency, safety, ergonomics, and performance. This also includes many new features designed for beginners, for everyday coders, and for even Scala experts to explore. And we'll also take a look at the planned roadmap and migration to Scala 3. Just for a bit of housekeeping, as always, today's webinar is made possible only by people like you, encouraging your company to become one of Lightbend's hundreds of happy customers, like our client Marlow Navigation, the creator of cutting-edge ship and crew management services based out of the beautiful island of Cyprus. So if you're looking to relocate to a sunny beach-filled environment, they are looking for a senior Scala developer with experience in Akka, Play, and Logom to join their fast-growing team in Cyprus. You can find out more about this position and other open positions with Lightbend customers on lightbend.com under the About tab. This webinar is being recorded and it will be shared with you next week. Because of some time limitations of this session today, we might not have time for very many questions and answers with Martin. But if you're an existing Lightbend subscriber, then you know that you can reach out directly to our Scala team and other engineering teams at Lightbend through the customer portal. And you can ask any additional questions, what ifs, how-tos, and best practices about migrating to Scala 3 there. All right, thanks for listening to my spiel. Let's hand it over to Martin Odersky. Martin, thank you so much for being here with us today.
Thank you for attending, and I'm excited to share what will be around the corner with Scala 3. So Scala 3 is now a concrete thing. It will be a reality fairly soon. Let me just go to the next slide here. Yeah, so here we see a roadmap. So where we are today is in June 2019. All the features that we plan to ship in 3.0 are fleshed out and have been implemented. So there's a series of implementations under the Dotty project name. Dotty is essentially the precursor for Scala 3 that first was used to try out things. So we did a lot of experimentation. Dotty existed for about 5-6 years where we did that. And now things are consolidating, and the Dotty code base, the Dotty compiler, will ship as the Scala 3 compiler. When will it ship? Well, it's going to be in final next year in 2020, but already this year we are going into feature freeze. That's when we ship Scala 3.0 M1, and that should be in fall of this year. So where we are now, I'd like to say we are in essentially feature envelope freeze. That means essentially we have all the features that we want to ship provisionally identified. We are now in a phase where we try them out large scale in our own code base. And while we do that, there might still be some changes that we foresee because we encounter some usability problem where we said, well, we could actually improve usability here or there. So we want to give us at least some months until we get confidence that what we have is actually also what we want to ship. And that is foreseen for fall 2019. Then we want to take about 1 year for stabilization. Stabilization means that we have to spec all the features. We have already made quite a lot of progress in the SIP Scala Improvement Process Committee, where we did a review of all the features that we have proposed for Scala 3. And essentially the SIP committee gave its feedback, and the features that we currently have been I won't say approved, but essentially seen and the SIP committee said they would be basically that they could foresee adding them to the standard, depending, of course, always a final specification and the final implementation. So basically, they have been sort of provisionally given the thumbs up. Of course, it's not just the spec; it's also the implementation. So we will work on more test cases, bug fixing in the compiler, and then migrating the open source ecosystem, starting with low-level libraries that we all want to get into, essentially a new community build that works on Scala 3. Finally, we also want to work on compatibility and migration tools, because the jump from 2 to 3 will be quite big. It will be, some of the things will not be backwards compatible, so there will be some breakage. We will work very hard to minimize that breakage, to make it rare and easy to fix, and to make hopefully most of the necessary fixes automatic with rewrite tools. So that's the goal, and that's essentially the number of topics we want to work on in the next year. So then, now that we have what's in it, when it will come, the question is what is in it. So what I want to do is give you not a complete tour of Scala 3. For that, actually, you have the documentations. So we have docs for all changes and new features at the link that you see here on the slide. So if you look at dotty.epfl.ch and then follow the docs links, you get it. So I just take you there right now. So here you see essentially the reference document, where we have the overview of what we want to, essentially what were the goals that we had for the language, and essentially what are all the changes. So what the goals we had for the language, maybe I can give you a quick rundown, was to say, well, we have worked on new and very solid, compared to many other programming languages, foundations. That means essentially type systems and calculi, where we actually know what we're talking about, because people have proved soundness and other properties of these type systems. And we were going to base the language on these foundations, so that has some effects on new types like intersection types, union types, type lambdas, and implicit function types. That was the first objective. The next objective was to simplify the language with to make it more approachable for newcomers, to make it reduce the gotchas, to reduce pitfalls and surprises in the language. So there's been quite a lot of work on that. There's also some work on restrictions, where we found that since Scala is a very unopinionated language, it gives a lot of choice to programmers. In general, I do believe that choice is good, that essentially nobody wants to essentially force programmers to use essentially one thing only. That's not what Scala is. But sometimes choice, we found that there are certain choices that turned out to be either dangerous, so in terms of soundness, or easy to shoot yourself in the foot, or where the choice was sort of unnecessary. You sort of just people didn't agree whether, let's say, you want to write a method in infix form or with a normal method call with a dot and parents. And there are good reasons for both, but the point is you shouldn't have to make this choice because it's unproductive in the end, and it's even more unproductive to discuss with all your teammates on what the right choice would be. I mean, these syntax things are essentially you just say just agree on something. So there will be some restrictions on that front, where the language is just going to take up a stand and say, well, we're going to do the things this way and finish the discussion. Finally, there has been also quite a bit of simplification on the language side, where quite a few things have been dropped from the language because we, over the usage over the last 15 years, we found out that actually they weren't used much. They did not really warrant the complications to the language. And also because we want to keep Scala fundamentally a language that is modest in size and quite simple. Scala, if you look at the number of features in Scala, it's actually not that many. It's just that you can combine them in very flexible ways. Okay, so you can browse the documentation at your own pace, of course. Let me just come back to the talk, and what I want to do, that instead of giving you an exhaustive and exhausting list of all these changes, I just want to essentially do a best of top 9 as it goes, top 9 features. So I want to ask the question, what do I think are Scala 3's nicest features? That question by itself is loaded because it depends on whether what your audience is. Are you addressing yourself to beginners, to everyday programmers, or to experts? So I want to have a category for each. I have a top 3 for beginners, top 3 for everyday coding, and top 3 for experts. And I'm going to give you my personal ranking, but I also did a Twitter survey, and I'll report on that. So what the people in the survey said. So what are, in my opinion, the nicest features for beginners? At that level, actually, most of the language stays the same, but nevertheless, a few improvements worth mentioning. The first feature is drop new. So in Scala 3, you can actually omit new from almost all instance creations. So you see where you have to write now, new string builder of ABC. In the future, you can just write string builder of ABC, or string builder with empty parents for the other call. You only need new to disambiguate in an apply method. So the issue is if you have a constructor, an apply method yourself that you define yourself, then if you inside the constructor create a new object, then in the end, if you leave out the new, well, you would call the apply method recursively instead of creating anything. So in these cases, you still have to write new, but in all other cases, you can omit it. New has become optional. One nice side effect is that you don't need to define a case class anymore just to get the nice constructor calls. In fact, it turned out that we saw quite a few people writing case classes just to get basically the free constructor call, where they didn't care about the other aspects, pattern matching or the convenience methods. So in the future, you don't have to do that anymore. And also, you could say it makes the language more regular that way, because where you don't need to write a new for case classes, now you don't need to write a new for any class. So that was my number 3. Number 2 would be top-level definitions. So in Scala 3, you can now write all kinds of definitions on the top level. So that means that you don't need package objects anymore. That was Scala 2's way to essentially emulate definitions on the top level in a package. Those package objects, you don't need them anymore, and in fact, they will be phased out. Not for Scala 3. In Scala 3, we strive to keep a very large common language subset, where of essentially a large subset where you can write in both 2 and 3, and they mean the same thing. But the plan is to go, as we progress in the 3 series, to start deprecating features that are no longer relevant, and where we have essentially good replacements. So in the future, what you can write is code like this. You can write package P, and then you can have type definitions and null definitions, method definitions, in fact, all kinds of definitions, also implicits, on that level directly. That also gives you a very nice way to unify scripting and languages, because what you see here, if you leave out the package P, it really looks like a script, and it can be executed also like a script. Number one for the beginner category would be no doubt enums. So enums are the simplest way to define new types with a finite number of values. Here you see a simple example, color. So you write enum color, red case, red, green, blue, and that's it. So that gives you a new type color and 3 constants, red, green, and blue of that type. That's the simplest case of enums, but you can actually make them quite a lot more powerful if you want to. So here's an enum that's essentially on a feature parity with Java enums. You write planet, and in this enum, the enums can actually have parameters, and the cases can essentially define specific values for these parameters. So in that enum, the enum would be called planet, and mass and radius are parameters, and then you would have the enum constants, Mercury, Venus, Earth, and Mars, which all essentially are planets with specific values for these 2 parameters. What you also see in this example is that enums can have fields, and they can have methods that you can write just in the enum. And furthermore, enums are also compatible with Java enums. So you can make a Scala enum be a Java enum just by extending Java lang enum. So if in that case, now planet would be a Java lang enum that can be used also, consumed also as an enum from Java. But enums actually are more than just Java enums. They're also ADTs. So ADT means algebraic data type, and the enum construct in Scala also covers these. So what you see here is an example of essentially defining a new option in a new way. So option, of course, is given in the standard library as a sealed trait with a case class sum and a case object num. But a shorter way to define the same thing would be as an enum option of a type parameter t, which happens to be covariant, hence the plus, and 2 cases. The first case is sum, where you have a parameter x of type t, and the second case is none. And in fact, that enum translates into the hierarchy of what I've shown you with option with the case class sum and an object, or in this case here, it's just a none that is a value of type option of nothing. So that what you see here on this slide would be the translation of what this enum option of t maps to. So one thing you've seen here is that the constants of an enum and the cases in the case of parameters, they all reside in the companion object of the enum type. So option would have option.sum and option.none. So sum and none would be nested inside the companion object of option. If you don't want that, then you can, of course, import them anywhere you want them at the top level. And in fact, Scala 3 also has a new statement called an export statement. So I could write export right after the option, and that would make sum and none available also as constants at the top level. So that was our reason for defining the enum constants inside the companion objects, that we say, well, we can always pull them out with an import or an export, but we would never be able to squeeze them back in if our default definition would have been as constants and classes aside the enum trait. So that's why it was done this way. Okay, so enums can do ADTs, but they can even do more than ADTs. They can also do GADTs. I don't know how many of you are familiar. GADT has this ring of academics and type acrobatics to it, but it's actually rather simple. So an ADT, what you've seen with option, let me go back to this thing. We have a base type option of type T, and then sum of T is a subtype of option of T. So it's just essentially at the same type parameter. So for each sum value, I have an option of value, and any option of any element type would have its sum type. So that's what we call an algebraic data type, or ADT. And in a GADT, the difference is that some of the cases might extend the base enum at specific types. So a good example for that is this tree type that you see here. So we have an enum tree of T, where the T is essentially the type of the tree elements. And then we would have cases which essentially give you a tree representing a simple language, as a structure of a simple language. So here's a case true. So we say the true constant, that's a tree of Boolean, and the false constant is the same thing. And then we would have a test is 0 that takes a tree of int and gives you back a tree of Boolean. And you have constants, a constant 0, that's now a tree of int, and the successor that takes a tree of int and gives you back a tree of int. And finally, what we have here is an if. An if takes a condition, which must be a tree of Boolean, a then part, which is a tree of T, and an else part, which is a tree of T, and it gives you a tree of T. So what you see here is that the cases extend the base type at specific type, and that's a GADT. And that's also possible with that enum syntax that you see here. And I think that makes enums sort of extremely flexible, more flexible than in any other language. So there are enum languages that combine enums with ADTs, but so far none that combined enums also with GADTs. So even in Haskell, which has essentially ADTs, GADTs are a different construct. So you write a GADT in a different way than an ADT, whereas in Scala, it's essentially all exactly the same construct, and they all map to the same things, namely sealed trait, case classes, and singleton values. So I asked the public before my Scala Days talk in June the question, what's your favorite Scala 3 features for beginners? And they actually agree with me. 56% said enums, 16% said top-level definitions, 23% said drop new, 5% said inline and alpha, but that was actually quite high because I meant infix and alpha, which are essentially the restrictions to infix methods. So the entry was so confusing that I was surprised to even get 5% of people voting for it. Good. So why enums? Why did the audience pick enums, and why did I pick enums? Well, I think there are lots of use cases, and they're becoming more common as we see more and more data-centric architectures. So I think we see more and more the idea to define business logic as a sequence of data types. And then I think case classes in Scala are great. They are definite improvement from normal classes and object-oriented types. But if I think by now people define so many of them, so many sealed traits and case classes, that even the streamlined syntax of sealed traits and case classes can become bulky. So enums are clearly an improvement in conciseness for these very, very common use cases. They avoid boring and repetitive boilerplate. And also they can grow from very, very simple, like color, red, green, blue, to very, very powerful, like the GADT of trees that you have seen. So those were the 3 top features for beginners. What about everyday coding? There are actually lots of candidates. It was hard to come up even with a short list. So I tried to do that, and I give you my list of favorite top 3s. Number 3 would be union types. So union types are something that came from the foundations of Scala, where we have the so-called dot calculus, dependent object type calculus, which is essentially gives you a mini Scala about which we can reason formally and with precision, and where we can prove some things. And that language had union types and intersection types. The union types are the natural complement of intersection types. Intersection types, you know, sort of from Scala, they are essentially the width in a type, the compound types. Compound types are a approximation of intersection types. They are intersection types are a bit purer and cleaner than compound types in the sense that, for instance, they're commutative. So for intersection type, A and B is the same as B and A, which wasn't the case for compound types. So you could say intersection types are cleaned up compound types, and their duals are union types. So union types are actually have quite a lot of interesting use cases on their own. So here's an example. Let's say you have two case classes, one for username and one for password, and you want to have a help function where you get the ID of your user, and it could be given as either one, either username or password. So you have this thing, and then you say, well, a user is, then you can just match and say, well, if the ID is a username, then you look up the name, and if it's a password, then look up the password. So of course you could use a common base class with maybe a case username and password could extend the same thing, user identification or whatever, but the point is often you didn't think about that. So if username and password came from different code hierarchies, then maybe nobody thought of adding a common base trait. The other possibility you could do is you could use an either type, so either username or password, but at least in this case, it would look quite a bit clunkier than what you have here. So username or password, they give you a very essentially low ceremony way to have unions of possible types, ad hoc combinations of types. What they also give you, and I think that's interesting, is they give you this idea that subsetting is subtyping. So if you have essentially a thing with three identifiers, let's say username or password or secret question or something like that, then what would be the case is that username or password would actually be a subtype of that because it's fewer possibilities. And that's actually quite useful sometimes when you structure systems. And the third argument for using union types is that unlike either, there's absolutely no boxing overhead. So they can be very, very efficient. So for high performance scenarios, sometimes that's actually the option that is fastest, and sometimes it actually matters whether you spend that extra box or not. So the other really nice thing about union types is that they work really well with with singleton types. So as you might know, in Scala 2.13, sorry, there's a new feature called singleton types, which means that you can use a constant as a type. So here you have a union type of 3 strings, click, drag, and key pressed. So those are strings on the value level, but they're also strings on the type level, namely the type click is the type that has a single value, the string click, and the same for drag and key pressed. So the type of command is then the type that has 3 values, click or drag or key pressed, all 3 being a string. And you can paramatch on that. You can say handle event, and you can do kind match, and then you say, well, if it's a click, then do one thing. If it's a drag, do another. If it's a key press, do the third thing. So that if you look at that and have maybe programmed some TypeScript, you say, well, I know that sort of thing. TypeScript does the same thing. And it's true, they have both singleton types and union types. And the reason why TypeScript has it and the reason why it's useful for Scala as well is really great for JS interop, because in JavaScript, the sort of the unstated informal type system makes a lot of use of these union types and of singleton types. And definitely in the JavaScript scenario, both of the union types and singleton types will play a big role. Good, so that's my number 2. What about number 2? Number 3, what about number 2? So for me, number 2, I believe, would be extension methods. So an extension method is a method that you can add to an existing class without defining a new class. So for instance, if you wanted to define a times operator on string, the way to do it right now is you would define essentially an implicit decorator class called which_string or something like that, and times would be a method in it. That works, but it's kind of clunky. You have to know about implicit classes, which are a form of implicit conversions, and it's fairly heavy machinery to get this going. What you see here is what I would claim is a much simpler way to do it. Let's just define the method as an infix method. So the way you do that is you just take the first parameter, the parameter that goes to the left of the dot or to the left of the star if it's an operator, so that would be a string, and then you write the thing you define, the operator, and then you define any additional parameters. So in this case, it would just be an int, and it would be followed by the definition of the method as usual. So then, since it's an extension method, you have to import it to be usable. Once you've imported it, you can write hello times 3 and use the method just as if it was an operator on the string class itself. So extension methods are essentially a simpler way to add methods to existing classes. They would replace implicit classes in that functionality. The number 1 for me is also probably the biggest change that Scala 3 contains, and that's our redesigned implicits. So the new syntax for redesigned implicits are so-called given instances. Let me introduce them by an example. So a typical example is ordering. So for ordering, we have type classes. So a way to express that in Scala would be we have a trait ord or ordering. Here on this slide, it's just called ord. And ord would have a methods like compare to and less than. In this case, we can already make use of extension methods directly and say, well, let's just define both compare to and less than as extension methods. So as infix methods that take a t and on the left-hand side and a t on the right-hand side and return an int or a boolean. Okay, so that was ord. Now we need an implicit instance of ord, let's say 1 for ints. So the new way of writing that would be, as you see here in the second block, you would say given int ord as ord of t, and then you would that would be followed by the definition of the abstract method compare to. So what given essentially does is, well, if I translate that to current Scala, that would be the same thing as an implicit object int ord, which extends ord of int. But it could also be, of course, that these given instances, they have parameters, and then in current Scala, I would have to use something else, like an implicit def backed by a class. Or it could be that they are aliases. Then again, in existing Scala, I would have to do something else, like an implicit val that is an alias of something else. So what givens give you is essentially a unified syntax for all of that. So they would say, well, what we do here is instead of having many different ways to add implicit as a modifier, I have a single way where I can state that I have a way to define a term for a type, as you can see here, this with int order. Oops, sorry. The next last block in the slide is the maximum function now that has to take an ordering, and it takes a list and it gives you the maximum of that list. So the way we do that is that we have given as a parameter clause. So maximum would say it takes a list of t given an ordering of t. So it really reads very well in the same way you would express this with natural language. And then since ordering of t is then available as a given, you can actually already use the less than method as an extension method again on ordering of t. So that was a nice integration of extension methods and these given instances. Okay, so the new design principles for implicits were to say, well, so far implicits did a lot of things and there were a lot of rules and people got confused very quickly. Also, there were lots of abuses. So to do better, what we want to do is we want to concentrate on essentially the core concept behind implicits, and that core concept is really term inference. So that means given a type, produce a canonical or given term of that type. Trade types for terms. So it means that instead of adding implicit as a modifier to many different constructs, changing the meaning of each in slightly different ways, we have a single construct to introduce a designated term that can be inferred for a type. And these we call these terms the given instances or just givens. So that's the idea behind it. I take you through some of the ramifications of that. So one ramification is it's really cool for type classes. Here you have one, let's say monoid. You have the type class semigroup and monoid, and here's a given instance, a type class instance for monoid. So you would just write given as monoid of string and then the combine and the unit methods. Compared to what you have to do today, it's dramatically simpler because today you'd have to essentially define an implicit class, an implicit def, and then another implicit class to essentially make these extension methods work. So here it's basically all rolled into this thing. And also what it essentially gives you is to say, well, we are not interested in the mechanics, how precisely you would construct this object. It's good enough that you have an object that has these combine and unit methods. I don't really care how you get that, because that object typically will be inferred by the compiler anyway. I just want to essentially communicate to the language my intent that I need an instance of monoid at type string, and that those are the two implementations. So we stay at a much higher level than before with implicits. Down here you have then a way I can use it. So a sum method can essentially takes a t which must have a monoid defined on it. So that's a context bound, which is of course known from current Scala, and then it would essentially do a fold left, and the is the new implicitly. So the monoid of t would say, well, the given instance of monoid of t, take the unit value and combine it. So what this shows you is that givens work out of the box with extension methods, and they provide a really slick syntax for type classes. But there's one other thing where implicits were used for, and that was implicit conversions, right? In fact, many tutorials for implicits started with implicit conversions because that's sort of the simplest thing that one could think of. Unfortunately, it's also a very dangerous thing. So what's wrong with this picture, this implicit conversion into string that essentially takes a string and gives you, sorry, that the title is actually very misleading. It shouldn't be into string, it should be string to token, but it doesn't matter because this thing is implicit anyway. Anyway, what's wrong with this implicit conversion? Well, I think it's way too easy compared to how dangerous it is, because if you have these conversions flying around, then you get a lot of feature interactions, and essentially the more you have, the more tricky things become. So since implicit as a modifier will go away, this kind of conversion will also go away, which I believe is a good thing. But sometimes you do need a form of implicit conversion. So what do you do? So what you will do in the future is there will be a standard conversion class, Scala conversion, which essentially takes the from type and the to type. And what you do is you have to define a given instance of that conversion class. So you write given as conversion string token, and then essentially you write what the apply method for that conversion is, because conversions are a subclass of functions, so they need an apply method. So you define what that should be. Or you could also use an alias like this. So you can say given as conversion string token equals new keyword, and that essentially would make use of the fact that the conversion is a SAM type, single abstract method type. So new keyword, sorry, is a lambda, and we know that already in current lambda Scala, you can essentially produce a lambda for a SAM type, for a type with a single abstract method. Okay, so what was the public vote for everyday coding? The public vote was actually in favor of union types, which was my number 3. So union types 45%, 24% extension methods, 16% revised implicits, and 15% opaque types, which I didn't have time to present, which are essentially another interesting feature of Scala 3 that can gives you a guaranteed box-free version of value classes. So why do I rank given so highly? Well, if we look at Scala, then I think implicits are clearly its most distinguished feature, but it's also the most controversial one. And I believe that given instances are a simpler and safer alternative. They emphasize intent over mechanism, make the idea of term inference more accessible, which is, I believe, the fundamental idea behind it, and discourage abuses. So that's why I think that if we sort of reload the whole thing with given, then we have something that we can state is, I believe, the right way to go about these things, and I expect great things to happen with that. There are also, I mean, it's not just a change in syntax, there are many improvements over current implicits. So I just run down the list. So in the new design, names don't matter. They shouldn't. I mean, once you infer terms for types, the names of these terms shouldn't matter. And in the new design, they don't. Nesting is significant, which gives you a way to achieve local coherence really easily. There are no shadowing problems, so all these have been eliminated by a change of rules. We have restricted the implicit scope to avoid some surprises. We have more robust prioritization, which gives you essentially more flexible ways to choose one implicit over another. There are no accidental conversions that could happen in current designs where you import, let's say, a map type from keys to values, and that if that is an implicit parameter, then that actually gave you an implicit conversion from keys to values for free, which is probably not what you intended. And the error messages have been greatly improved in the compiler. So hopefully this should be a much better experience when dealing with implicits than before. So migration, so the current implicits are still supported in 3.0 and will be deprecated from a future version, maybe 3.1, maybe later, but from 3.1 on they might be deprecated. And there are also special provisions for cross compilation where essentially the old style implicits can also be used with new style arguments and imports. Okay. So the hardest thing actually was naming them. So the design of them has been solid for 6 months, but how do we call these terms that get inferred for types? And we went through a long list of names. The last remnant was delegate for it. So I think we will probably stick with given because that seemed to have the largest support from the people who have seen it and also the SIP committee. So I'm reasonably confident that we won't have other changes of names, but I could also always be wrong. But I mean, names don't matter. A name is just a name. So that brings me to the nicest features for experts. So since Scala 3 actually also puts meta programming and macros on a new basis, there's lots to choose from, and it was difficult to pick a winner. For me, the number 3 win was match types. So a match type essentially does meta programming, computation on the type level in a functional way. So as an example, let's say you have an enum tuple, which can be empty, or a pair of head and tail. So that's essentially, you could also say age list, which is sort of the current term for this thing. And then you want to define an operation to concatenate two tuples. And not only do you want to define the operation, but you also want to be able to say what type it has precisely. Now, of course, the type of concatenating two tuples depends on what these tuples are. If, let's say, one is a pair and the other is a tuple, then it would be a quintuple. And furthermore, the types of the quintuple would be the types in the pair and the tuple. So we have to compute to actually produce that precise type. And here's how you would do that. So I can define a type concat, where I can, that takes two type arguments, xs and ys, both of them tuples, and then I can actually match on the first one, xs. If it's empty, then the concatenation is just the second one. If it's a pair, then the concatenation is a pair again, whose first element is the first element of xs, and whose tail, those remaining elements, are the result of concatenating the remaining elements xs with the second argument ys. So you see, we can compute on the type level. So far that was possible to do, but in a very roundabout way, using implicits. So essentially all the age list implementations that we have, they were essentially, instead of saying concat with two type arguments, they were concat had three arguments, namely the type you put in, the first type you put in, the second type you put in, and the result. That was the third type parameter. So going from 2 to 3 means going from functional to logic programming. So these things are essentially predicates which relate the arguments and the results. And age lists and implicits generally look a lot like programming with Prolog. But I would argue that in particular in a functional language like Scala, a functional way of expressing these types is much simpler and intuitive. And that's why match types are a really nice way to express these things. Number 2 for me is typeclass derivation. Typeclass derivation is a way to define typeclass instances for data types, for essentially case classes, sealed traits that have case classes, or enums, which map to sealed traits with case classes. And so far you would use a macro-based library such as Shapeless or Magnolia for it, and these libraries were known to be quite heavy, in particular to sometimes be quite heavy on compile times. So in Scala 3, and also those two libraries were using very advanced features of the current macro system, which always was experimental and will go away. So in Scala 3, we will actually make them make the basis for typeclass derivation primitive in the language, and we will have very nice syntax for that. So the syntax we have is essentially, you can derive just as nicely as you can extend. You can have let's say an enum tree of T, and you could say it derives the equal class and the ordering class and the pickling class. So it's just as easy as saying extend equal ordering pickling if those would be super traits that you could extend from. And what that generates is essentially 3 given instances of a type parameter T that is now itself bounded by the type class equal ordering and pickling. So the given instance would be for equal and ordering pickling each, and they would each call a method called derived. So equal.derived, ordering.derived, pickling.derived. And those derived methods, they are methods that type classes have to define. So here's a way you could define them directly. That's a low-level way that's actually very, very efficient at runtime, but can generate a bit of code. So you could use an inline method, which is essentially Scala 3's new way to write macros in a very simple and principled way. And the inline method gets a so-called mirror, which is something that the standard library would provide. And then essentially that's what you would do. So don't be scared of this code. So that code is essentially something that you would only write if you are in the business of essentially providing type classes to others that have automatic derivations like that. So if you want to do that, if I want to say, I want to define unequal type classes that should be derivable automatically for all data types, then you would be in the business of writing that. Or you would use essentially a deriving framework, which makes it simpler for you. And that could be essentially shapeless, for instance. So there is a version of shapeless 3 by Mal7 that is based on these primitives, and that does then most of the work for you. Okay, so to my number one then would be functions everywhere. So Scala distinguishes methods from functions, and with good reasons, because essentially that's also the way to unify objects and functions. So the price for unifying objects and functions is that you have to distinguish methods from functions. But what we want to do is we want to essentially still give the fundamental capabilities of methods also for functions, that we don't lose anything going from methods to functions. And in Scala 3, that's achieved to a much larger degree than in Scala 2. So function types in Scala 3 can be dependent. So here you have an example of that, where you want to have, let's say, a graph, and it has node and edge types, and then you want to have a method that takes a graph and it gives you the node type of the graph. So as written as a method, you could of course say take a G graph and return G.node. But if I want to lift this into a function and a function type, like the type of functions that do that, then I need a dependent function type. So I need to have do a function type where I can talk about the parameter G in the result type of the function. So that's called a dependent function type, and that's something that Scala 3 has. The same thing holds for polymorphic. So methods can be polymorphic. They can have type parameters, of course. Functions in Scala 3 can do the same thing now. So a polymorphic function type would be written like this. So you can have now type arguments written in brackets that give me function types that are polymorphic. And finally, methods can, of course, be implicits. So function types can be the same thing. So they can be implicit function types, like the one that you see here, where we have a type that goes from execution context to some t, and the execution context would always be automatically provided. So it would be a given parameter. So all these three things make Scala a lot more regular. And also powerful. Regularity means power for expert users. That essentially they can then essentially raise the level of abstraction and do more interesting things. Good. So what was the public vote? So the public vote was, maybe not surprisingly, the out-of-the-box thing. So having native type class derivation won the public vote with 51%. Match types and implicit function types shared second place, and the inline and staging, which I didn't show, was well, I did show it type class derivation on the one slide, so that was got third place. Okay, so let me just show these things together in some synergies, how these things can play together in Scala 3. So here's a little thing that I've wanted for a long time. So Scala 3 has an ensuring decorator, essentially, so you can put ensuring on anything. Well, actually Scala 2 had that already, but what's the new thing is this result thing. So what I want to do is I want to have essentially post conditions or contracts where I want to write things like list of 1, 2, 3, take the sum, and make sure that the result is 6. So the problem is, well, where does this result come from? How can we talk about the result of something that is essentially to the left of the dot without making a lambda? A lambda would be possible today, but would make it a lot clunkier. So the idea is we can use a combination of opaque types, the new given types and given implicit function types to work together. So the idea is that we would get the ensuring and the result from an object called postconditions. So here's what ensuring is. It takes an arbitrary type T, and it takes a condition. And it takes a condition that takes a wrap of T to Boolean. And that is an implicit function type. So what it does is simply it does an assert of the condition with the given parameter, the x. So it says, well, is the post condition condition does that hold for essentially the prefix of ensuring the result? That's the result of this. Okay, so how do I get result? So result says, well, I need to be given a wrap of T and I give you back a T. So wrap is essentially wrapped result. And where does the result come from? Well, because ensuring takes an implicit function type like that here. So what it would do is it would essentially produce here a lambda, an implicit lambda, that essentially takes a wrapped result, and that wrapped result gets passed by the ensuring here. So the end result is that I have very, very nice end user syntax where I can talk about these things like result, and it's made possible by essentially a conjunction of these primitives. And furthermore, the other nice thing is that that's a zero overhead abstraction. So because I'm using opaque types, there's not a single extraneous boxing anywhere, and it's as efficient but more streamlined notationally than if I would just write out the assertion by hand. So with all this, the question, of course, is, well, is Scala 3 a completely new language? There definitely seem to be a lot of new things. And the one answer would be yes. There are many language changes, including feature removals. The new constructs improve user experience and onboarding. So it's not just essentially some details for experts. It's things that I looked at essentially my intro course to Scala, and I would say, well, from at the latest week 3 on, I would use new features, namely enums. So there are really things that I have to do for new things as well. And that also means that books will have to be rewritten. So for Scala 3, some of the things will be quite different than for 2, and it would be good to have new tutorials, new courses, new books, and I will probably have to do it myself as well, write a new edition of programming in Scala and do a new course for the MOOCs. But you could also say, no, it's not really a new language. It's still recognizably Scala. It looks like Scala. All core constructs remain in place, and there's a large and practical common subset between Scala 2 and Scala 3. How do I know that? Well, because our own compiler, which is close to 100,000 lines, is actually, or was until last week, written in that practical common subset. Because it was written in the common subset, we couldn't really experiment with all the new features, but it wasn't constraining at all. So that compiler got first compiled with the Scala 2.12, and then it compiled itself. So all the features in the compiler are valid under both 2 and 3. That also means it's very easy to have programs that cross-build, and besides the Scala compiler, there are also other large programs that do that. So the largest so far is Scala Test, which is about 600,000 lines of code. So Scala Test, we have a version of Scala Test that cross-builds between 2.12 and 2.13, and 2.13 and not yet, but soon enough, and 3. So I guess the real answer is it's a process. So In Scala 3, we keep most of the constructs in 2.13 alongside the new ones. And that means that for Scala 3, not that 3.0, not that much will really change or has to change. Some constructs will be deprecated in point versions of Scala and will be phased out in the long run. So that also means that we will have some temporary duplication in the language. So for some time on, both old constructs like implicits and new constructs like givens will be part of the language. But as we hopefully phase out the old constructs, we will achieve hopefully as an end result a more compact and regular language. So if you look at some of the replacements, and what we see is we have exports and top-level definitions that will replace package objects, givens that will replace implicit defs, vals, objects, and implicit conversions. Extension methods can replace implicit classes, and inline staging and match types are more than a match for the current macros. One criticism that we heard a lot was, well, why so many features at once? Couldn't you have rolled it out bit by bit over many releases? Well, one critical point here is that Scala 3 is, like I said, when the books will be rewritten. So essentially, since there are changes that simplify and restrict the language, you want to put that basically in the tutorials already. You don't want to have in your Scala intro something that basically is about to be deprecated, and you don't want to miss something that would make things much simpler for beginners, like Enums. So that means that we have essentially this point in time, which maybe comes every 10 or 20 years, where you say, well, books will have to be rewritten. It's really sort of a big change to the language. So that means that we have to get a feature in now if it affects foundations, if it simplifies life, especially for learners, and if it replaces existing features. And we concentrated on, for our feature set, on precisely these things. So we prioritized to put in things that affect foundations, simplifications, and restrictions, and we have fairly few things that actually add power and expressiveness. There have been many more proposals, and maybe they will come in future versions, but there essentially our razor was to say, well, no, if it just essentially gives more convenience for special cases to experienced developers, then it can also come in a later release. So how to get there? So we have source compatibility for a large common subset. We have rewrite tools that handle much of the rest. So that's why I think that the situation is much better than the often cited case of Python 2 versus 3. Also because we have essentially two other assets, that's static typing and binary compatibility. Static typing, of course, gives you essentially the assurance that you have caught the problems, and we will make very sure that essentially any changes do not affect the runtime without also affecting the types. So we will not slip essentially silent runtime changes in the language if we can avoid it. The changes that are there are essentially some syntax and types, and all these can be caught by the compiler. And the other advantage is really binary compatibility. Already today, Dotty, so Scala 3's precursor, can link with Scala 2.12 class files. So we can work out of the box with Scala 2.12, and in a couple of months we change the switch and make that the Scala 2.13. So that means we can already have Dotty modules that sit on top of Scala 2 modules, and we can freely mix these artifacts. In the future, what we want to achieve is essentially make that both ways, so that Scala 2.14, the next Scala 2 version, should be able to also read Dotty, interoperate with Scala 3 modules. So that means we can have essentially stacks where we have a mixture of Scala 2 and Scala 3 modules, and that will mean that essentially you can migrate components at their own natural pace, and you never have to make sure that all your system components are in sync here. So that's the big promise in there. There's one caveat, and that caveat is Scala 2 macros, because Scala 2 macros won't be supported. So that means that if your library uses Scala 2 macros, then there has to be essentially a way, essentially a Scala 3 compatible version that uses Scala 3's new macro features to achieve the same effect. So you will have neat modules that work for either Scala 2 or Scala 3. So all that is possible by having essentially our own interchange format called Tasty that essentially represents the Scala 3 at a very high level way and gives you essentially all the information about a type-checked Scala 3 programs. That also should enable things like cross-platform compilation directly from the Tasty, and that also gives you essentially the symbolic information between the 2 and the 3 series of the compilers. So the plan is for Scala 3 is then to keep this Tasty format binary compatible over the whole 3.3.x series. So that means that compile from Tasty would allow code to migrate without the current problems of binary compatibility. So while we have undeniably challenging problems to solve to migrate from Scala 2 to Scala 3, the hope will be when we are at Scala 3, essentially the recurring binary compatibility problems where the whole world has to reboot at every major version will go away. From Scala 3.1, 3.2, 3.3 on, essentially the interchange format will be Tasty and that won't change. So that's essentially a thing that we will commit to for the 3 series. So that brings me to the end of the talk. You can try it all out at the URL that you see, .e.epfl.ch. We have a new version every 6 weeks. So right now we are still in the area where we iterate fast. But like I said, the feature envelope is fixed. So the features that you see now are the features that we would expect to see more or less unchanged, with probably some minor changes in the final version. Thank you.
All right, Martin, thank you so much. This was a very enlightening and revealing talk, especially for, I think, a lot of beginners out there that are looking to get more involved with Scala 3. As I said earlier, we are out of time for today, so we're going to have to leave your questions, of which there were a nice handful. We're going to have to leave your questions for next time. You can also hit up the Scala team on Twitter. Their handle is Scala_Lang, and that's a good place to get some quick interaction for some of the lighter questions that you have. So thanks everyone for joining us today, and Martin, thank you so much again for making the time, and we'll let you get back to your evening.
Thank you.
All right, bye-bye everyone.
Bye-bye.